This is Adding Houdini to Your Arsenal episode 3. Today I want to introduce you to VOPs. But before we start, let's customize the interface a little bit more. I want to get rid of the parameters view, just to have more space for the network editor. But of course I need the parameters. If I lay down a GeoNode at the moment, I don't have any parameters shown. But if I hover over the network view and press P, I get this overlay pane that uses less space than the parameters window, but displays the same parameters. So for today, I prefer this view. To get started, dive into the Geo1 node, get rid of the file sub, and lay down a torus. To have some geometry to work with, let's up the subdivisions to, say, 24 and 48, just to have some geometry. So, inside of Houdini, all these operators here are pre-compiled, meaning programmers at SideEffects coded these operators and then packaged them such that they are executing their function. They share a common geometry interface, as I explained last time, and they know how to read the geometry that is coming in, and then they execute their function. But inside of Houdini, there is a different kind of operators, VEX operators. These are operators that you can design on your own using the inbuilt programming language of Houdini called VEX. VEX stands for Vector Expression Language. You can append a point wrangle and connect the geometry, make it visible, and here you can write code. For example, I can state add P is add P and then plus a vector, let's say 0, 0.1, 0, and that will push up my entire torus by 0.1. That is coding. A lot of visual people, though, don't like coding too much. And that is why Houdini introduced a different way of coding called VOPs, VEX operators. So instead of using wrangles, you can use VOPs by laying down a point VOP. This point VOP here can be used to do exactly the same thing, but without writing code. Instead, it is a new network type, and inside you find different nodes that you can use to do your programming. So append this here, make it visible. The torus snaps back to its original location. And if you dive inside, you find these strange-looking nodes here. So what are these? These two default nodes are in charge of reading data from the incoming geometry and writing data to the geometry that is currently processed. This here is a point VOP. That means whatever you do here inside of this network gets executed for every point of the object that is connected to the input port. These ports here are the different informations you can gather from the incoming geometry. The names are abbreviated. You have some learning to do here. You have to just remember what all this means, because nobody is telling it to you. P stands for position, as you might have guessed. V stands for velocity. Force is force. Age is age in case of incoming particles. Same holds true for life and ID. CD stands for color. It's abbreviated CD because it comes from the shading context where it stands for color diffuse. Then you have UV, N is for normal, the global time increment, the current frame. PT num is the index of the currently processed point, though it is the number that you see if you turn on point number display, this number here. And then vertex number, in case you are using vertices. NumPT is the amount of points that is coming in. NumPrim is the amount of primitives that is coming in, and NumVertex is the amount of vertices coming in. And then you have these brown ports here, op input 1, 2, 3, and 4, referring to the 4 geometric input ports of the network here. So if I go up one level, you see I have 4 inputs here, and these 4 inputs are reflected here as brown ports named op input 1, 2, 3, and 4. And I think I missed primnum. Primnum is the index of the currently processed primitive, in case of a primitive VOP. So from this node you can read data, and this node is used to set data. Here we have a subset of these ports, P, V, force, CD, and N. That are the standard attributes that you can write to To do the same thing we just did in the wrangle, what you can do is create a constant. A constant is just a number. But in my case, I want a vector, because points are vectors. 3 numbers define a vector, and 3 numbers define a location in space. This is called the data type, and it is indicated by the color coding of these ports here. This green color means that the value is a vector. That blue color refers to an integer, and the light blue color is a float. And then these brown ports are a handle, a link to geometry. So now that I created this node here, let's switch constant type from float to something different. We need a vector in our case. You see, as soon as you open this menu, you get a long list of data types, and we choose vector. Now the port turned green, and I have 3 numbers here. I want to move the point of the torus up by a value of 0.1. That is what I did in the wrangle. So let's put 0.1 in the y field here. And now I want to read the position of the points, add this value to them, and then set the new position back to the points. So let's lay down an add node, because we want to add together vectors. And notice that the input port of this add node is white, meaning that the add node can handle different data types. And the moment you connect the first wire into this node, the type of this port will be determined, and it will change color to reflect the data type it is using. So we want to use the position of the points. You see, as soon as I drag this in, the input gets this green color to indicate that this is a vector. And I can add 0.1 to this. And now I use the sum to set the p value. And you see the torus is moved up. So now I can go in here to the constant and can change the value, and the torus is moving up and down because this is executed live. As soon as I leave the operator, as soon as I press U, the code that I laid down inside of this network using nodes is compiled, and now I have a compiled operator that is executing as its C++ counterparts. I can name this, let's say lift, and reuse it by copying it. Let's get rid of the wrangle. Nobody wants to use wrangles if we can do VOPs. Technically, the way this works is all these nodes just encapsulate vex functions. So in reality, this add is just laying down a piece of code, a snippet of code, into a program in the background. Same holds true for this constant. And you can actually see this code if you right-click on the VOP and say vex, VOP options, view vex code. Then you get this very verbose list of stuff. And that is the program that your VOP operator is writing in the background. So this is what gets compiled, and this is what is executed. That means, in reality, VEX and VOPs is exactly the same. VOPs is just an interface for VEX. Instead of writing, you can use nodes to code, and that is a great thing. VOPs come in very handy if you want to work with noise. So let's do this. Maybe it's a little bit easier to see what we want to do if we use a grid instead of a torus for this example. So lay down a grid, size it to 1 by 1, like so, and let's create a lot of subdivisions, let's say 400 by 400, such that we have a lot of points. By pressing Shift and W, you get rid of the wireframe display. Nice clean grid, and now let's append our VOP to the grid and name it noise and make it visible, dive inside. And it's moving the grid up, of course, because it's executing this function. Let's get rid of these nodes. We want to put noise into the color of this grid. The very first idea that comes to my mind when thinking about noise is using a random value for every point. That is easy to do. Just lay down a random node. That is a random function. It has an input port called position and an output port called rand. For position, we can use the point number, because the point number is different for every point, such that this random node will generate a different random value for every point. As soon as I connect this, you see again the color switches to the darker blue to indicate that this is an integer now. But the random node is generating a float value. And I can just connect this float value to CD, and you see immediately you have random values of color on the individual points. If you look closely, you see that this line is dotted, and that is because the data types do not match. This random value is a float, and CD, color, is a vector because it has three components, R, G, and B. But Houdini understands or knows how to convert a float into a vector automatically, because it just uses the same value for all the three components. That's why this random noise is black and white, and that is what this dotted line is indicating. It's indicating that a type conversion is happening, and that Houdini is automatically converting the float to a vector. We can do it by hand if we lay down a float to vector node, like so. Now you have three inputs for the three components of the vector. You can connect all three, and then the vector to CD, and you see now you don't have any dotted lines anymore because you did an explicit cast. So you cared about casting the values on your own. Great. But that is just random values. But these random values are not very useful. Usually you create noise to mimic natural phenomena or to vary attributes of a surface. If you look around yourself, stuff is not varying randomly normally, but it is varying smoothly. Near to your current location, the values are similar, and only if you are getting far away, the values change dramatically. With this random here, the values are changing all the time. So let me introduce you to the concept of Perlin noise. We can lay down a noise operator called turbulent noise. And if we connect P to the position and noise to our three vectors, like so, you see now we get noise on our plane. This turbulent noise operator is capable of generating different kinds of noises. The noise type is specified here, and let's switch this to original Perlin. That is what you get. At the moment I get specular in my viewport, and that is a little bit distracting, so I just press this button here to turn off shading. Now I have the values only. And you see, Perlin noise, I have this black hole here, and that is due to the fact that Perlin noise creates values in a value range between -1 and 1. And this black area is just the values that are less than 0. And colors less than 0 cannot be displayed. That is why everything is black here. But how does noise work? Let me take a little detour to explain noise to you. In Houdini we use two-dimensional noise because we had a two-dimensional plane, but to understand the concept it's maybe a little bit easier to use 1D noise. So if I look at the very first row of points from the side of the plane, I have a one-dimensional thing. So with random, I have this axis here that is the, say, x-axis. And I have my points here. And now for every point I generate different values. And these values are large and small and large, totally random. Like so. That is the random function. What I want is, I want values that vary smoothly. So what I can do is, if I create a new axis, I can use something called a lattice. What if I only generate values for points that are spaced apart? So let's say I want a value here, and there, and there, and there, and there, and there. Now I generate my random values, let's say like so. Random values. Great. But what about all the points in between? Well, what I now can do is I can interpolate these random values. So I can fit a cosine function through these values, which gives me a curve. Like so. Shitty drawing, but you get the point. And that is where noise is starting to appear, because now the values are varying smoothly. They are still random values, but not everywhere. locally the values vary smoothly. Perlin noise does something even smarter, because it does not define random values, but it defines random slopes. Perlin noise uses a lattice to space some points, and then it defines slopes, the slope of tangent lines, and it defines these slopes randomly, like so. And now it fits a curve such that curve slopes exactly like these random slopes indicate. And that is the resulting function. This is how Perlin noise is generated. And as you can see, because I have slopes now, the curve always goes into the negative domain. So it's positive, then it goes negative, because whatever slope I pick, I always have to cross the x-axis. So that is why Perlin noise outputs values between -1 and 1. And that is the reason why you have this black area in Houdini. The frequency of the noise is the spacing of this lattice. If I generate the same thing, but space my points further apart, like so, then I get a larger frequency. And if I use points that are very close together, then I have a higher frequency, let's say like so, like so. If I now interpolate this, you see that I now have a higher frequency of noise. The spacing of these lattice points determines the frequency of the function. Then I can scale everything, so I can take this curve here and just scale it, like so, and so on. You see, by scaling this, I can determine the amplitude, because the amplitude is how far the values go in the y direction. That are the two properties of Perlin noise. But the curve that results from this operation is not totally interesting, because of course it's smoothly varying, but in reality stuff is often fractal, meaning that it has some self-similarity to it. And Perlin noise uses a nice little trick called octaves to mimic that behavior. So what Perlin noise does is it generates a first layer of Perlin noise, let's say something like this, and then a second layer of Perlin noise is generated, but with the doubled frequency. So frequency times 2. Frec is 1, and here frec is 2, like for example so. And at the same time, the amplitude is halved. Amplitude is 1 here, and amplitude is 1/2 here. And now these two frequencies are added together. So if you add them, you get something like that. Of course, that is not exactly correct, but the waveform I generate here is added on top of this main waveform, giving little details to this waveform. And if I continue the process with doubling the frequency to 4 and multiplying the amplitude by 0.5 again, so 1/4, and then add it up and continue to go on, I get more and more, I get smaller and smaller details, and the curve looks more and more interesting. And that is a concept of octaves of Perlin noise. So let's switch to Houdini and see this in action. If inside of Houdini you click the turb noise operator and go to the parameters, you find these parameters here. And you have the roughness and the turbulence. And the turbulence is the number of octaves. At the moment it is set to 5. And the roughness is a parameter that determines what happens to the frequency and the amplitude from one octave to the next. So because the roughness is set to 0.5, the frequency gets doubled and the amplitude gets halved in the process. So if I dial these down to 0, you see that I end up with 1 octave of Perlin noise. The frequency determines the size of the features because it controls the spacing of the letters. So if I go higher with the frequency, you see that more details appear. Nevertheless, the concept with the octaves is still valid because these are dependent on the starting frequency. But you don't have to use this inbuilt function here. You can do exactly the same thing by hand, just to understand it better. So if I dial this down to 0, I have just 1 octave of Perlin noise. I can now by Alt dragging duplicate the operator. And let's say I start with a frequency of 5. So let's do what we just found out. Let's double the frequency to 10. And let's halve the amplitude to 0.5. And now use the add operation to add both together. Like so. I will directly connect it to CD because that is faster. And now I can do this again, adding in another octave, doubling the frequency to 20, halving the amplitude to 0.25, and just using the third port here on this add node, adding it in. And let's do it one more time. Double the frequency, halve the amplitude, like so. And you see, that is what you get. If we duplicate the turb noise once again and just set the turbulence to 4 directly, connect this one to CD, you see it's pretty much identical. The only difference being the brightness. But in principle, this is exactly what happens here. So that is what is hard-coded here inside of this turb noise. And if you happen to use another noise operator, because there are several, like for example the periodic noise, you will find that the periodic noise is not capable of doing these octaves. It just generates one layer of Perlin. So if you want to have octaves with periodic noise, you can now do it by hand. Because it is more convenient, we will get rid of all of this stuff, delete the random, and just stick to the turb noise. The turb noise is generating negative values at the moment. We want to map the range of output values to the range between 0 and 1 to be able to really use it as a color. For this, we have the fit operation, fit range. What this does is it provides you with 4 input ports, source min, source max, dest min, dest max. And that just means take the value, and then if the value is 0, map it to 0. If the value happens to be 1, map it to 1, and interpolate in between. So if I now connect the noise to this value port and the value port to CD, nothing happens because the ranges are identical. But if I change the source to -1, I now map everything to the space between 0 and 1. So I normalize the noise, which is looking a lot better. But I not only can use noise for shading or for setting the color, I can use a displacement effect too. For this I have a node called displace along normal. What this node is doing, it's taking in the normal and the point, and then it's moving the point by this amount here. For this to work, I have to connect the old position into this node, and then I can connect the new position into P. Nothing happens at the moment because the displacement amount is set to 0. If I go up with the displacement amount, it works. Maybe you're asking yourself, why is it working? We did not connect the normal. And we can connect the normal. It's just that warps work like this. If the normal is not connected, then it tries to use the normal automatically if it finds one. So this is just a convenience function. To make it clearer, it is maybe a good idea to connect it. So now I can displace this, and it's just moving in the y direction because it is a grid. But what happens if I don't use a static amount, but I use my fitted noise as an amount? Then I get this, looking interesting. Switch back to shaded mode, and you see we generated a nice little terrain, like so. But there is more to working with noise, because at the moment these values are varying smoothly. But what if I want to influence the look of this terrain? Well, first I can dial down the destination max value, and if I do so, the displacement is not that strong anymore. I can do exactly the same thing if I go to the displacement and use this additional scale parameter. It's really just multiplying the values. So if I set it to 0.5, the displacement effect is only half as strong as before. But as this is all just values, I can use a function called gain on them. Gain is just a function, a 1D function. But as this is just float values, it will happily work. So if I connect the output of this fit node to my gain function, and then the gain function to the amount, I get additional control. What I now can do is I can control the steepness of my terrain. If I go up with the gain value, everything is very flat, so the stuff is varying very flat. And if I go the other way around, I can increase the contrast. Why is this? Well, the gain function is nothing special. Let me quickly show it to you. I found this neat little website visualizing the gain function and the bias function, which are brothers more or less. So if I switch here function to gain, you see at the moment with parameter 0.5 it's just the diagonal. But if I go up with the parameter, I create this S-curve. And if I go in the other direction, it's going in the other direction. And that can be used to remap values, like here with this gradient. If I go to 0.5, you see the gradient is linear. But if I remap it, I can flatten it out or make it more contrasty. And exactly the same thing happens with our noise. I can use the values that are linear and remap them to be S-shaped. And by doing so, I can control the contrast. The bias function is similar, but it does not do an S-curve, but it just does something very similar to a gamma curve, more or less. So it creates a knee here or here. Such that the values are not linear anymore, but they are increasing very steeply, and then they are slowly fading out, or the other way around. The bias function is another nice possibility to work with our noise. So let's see this in action. That is the gain function, which is generating this S-curve, and which allows us to shape our noise. Or I can use the bias, which is present here in VOBS2. And if I wire this through the bias, I can now create a noise that is very, very flat, or a noise that is very, very steep, like so. So by using this, you can remap the values that come from your noise. But these functions are not very visual, so let's get rid of them. There is another possibility, and that is called the ramp parameter. As soon as you lay down a ramp parameter, you are presented with this interface here. And as a default, ramp is used to create colors from a float value. So the input is float, but it outputs a color or a vector in this case. But you can change this behavior. What we want in our case is to use a float value as an input and a float value as an output, because we want to remap the float values. So we can switch the behavior of this ramp parameter node to spline ramp. Now we get this interface here. We can connect it up, and now we can draw the curve. At the moment, everything switches to 0, and that is because the ramp is set to 0 everywhere. This here is only the default. If you want to alter the ramp, you have to go one level up, because the ramp is a parameter node. What it does is it adds the parameter to the interface of the VOP itself. So now that I laid down this node, I have this ramp parameter here. And you see the ramp is set to 0 entirely. That is why everything vanished. You can click on this little field here to expand the interface. And if I move the second point up, you see I get back to where I was. That is the noise I had before. But what I can do now is, by clicking on this curve here, I can introduce new points. And by doing so, I can control exactly what happens to my noise. For example, by creating a curve like this here, that is flat, I can create plateaus. If I move this more to the bottom, the plateaus are not so steep anymore. And I can do the same thing for down here. And that really starts to look interesting. So what happens is this ramp node reads this ramp parameter from the VOP itself and applies it to the values that are passed through. So by doing this, I can shape my noise however I like. So instead of using bias and gain, which might be easier because it's just one value, you can draw the curve you want to use to remap your noise. Working with your noise does not stop here though. Let's for a second go back to the original noise output for color, and I cut the connection of P to P to just see the color. Remember that these values were positive and negative. What I can do now to create another visual type of noise is to fold the noise over. At the moment the function is going up and down into the negative domain, and I can use an absolute value node to fold it over. The absolute value will get rid of the sign, so it will just keep the value without the sign. So it will reflect everything that is negative to the positive side of things. So let's connect this and the absolute value to CD, and you see now I get this very interesting noise type where I have these veins going through the pattern. And that is due to the fact that everything that is 0 stays 0, but all the negative values are reflected over and are positive now. So if I do that, I don't need the fit anymore because everything is positive now. And if I connect this to my displacement, let's see what this gives us. And this gives us valleys and mountains. So if I temporarily get rid of CD to see this better, you can see that I now have very, very steep valleys. I can switch this over, just invert it by using the ramp. So if I now connect the ramp to my absolute value and this to the amount, go up one level and reset the curve. To reset the curve, you can drag these markers down and then they will vanish eventually, like so. And if I want to reflect everything, I want to drag the very first point up, so everything that is 0 should be 1, and the other way around. By doing this, I get these interesting ridges here. Let's decrease the effect a little bit, and if I now map the curve like so, you see I can generate sort of a mountain landscape. Let's remap that further, like so. At the moment, all the remapping is linear. That is due to the fact that the interpolation of this ramp parameter is set to linear. But I can change this on a per point basis. So if I select the point, the very first point, and then the other ones, with Shift, everything is yellow to indicate that it is selected, and now I can switch to B-spline interpolation, which is a smoother interpolation. Now I can alter the curve in a smoother way, like so, for example. And let's give a little ceiling here to the noise, and you can create very interesting structures by doing this. Or we can go up on this side to raise the intermediate terrain. Very cool. Maybe decrease the frequency a little bit to see this better. And you see, I get a rich terrain with veins running through. So I have now the possibility to fold the noise or to use it straight with the fit. And to be able to switch between the two, I can of course just wire this here in, maybe change the value range to reflect the same value range by putting 0.5 and minus 0.5 here. This is a terrain without the folding, and this is a terrain with the folding. To have both in the same network, I can use a switch, a two-way switch. The two-way switch has three inputs, input 1, input 2, and a condition. And it decides which input to pass on to the result by the condition value. The condition is an integer, and if it is 0, it uses one input port, and if it is 1, it uses the other one. So if I connect both of these nodes here to the two inputs, I now can lay down a constant, switch the constant to integer, and connect it to the condition. And then I use this result for my ramp. And you see it immediately switches to the fit node to input 2 because the value is 0. But if I now change the value, I can control if I want to fold the terrain or if I don't want to fold the terrain. So now we build a little operator that has quite some control over our noise. I have folding here, then I have the remapping, and in the end I have the displacement effect. For the next thing that I want to introduce, let's go to the turb noise and dial down the turbulence to make this very, very simple. This is a very simple function. Looks very interesting too with the folding, because the last thing that I can do with my noise is to warp the input space and thus warp the noise. At the moment it's just a standard Perlin noise generated as I explained to you, but it is sampled uniformly. So the noise value is calculated for every point in space, and all the points that I use for calculation are the points of the grid. They are regular and run here over this surface. But what if I change the input points? I can lay down a new turb noise. And the turbulent noise is not only capable of generating float values, but I can change the signature to generate vectors. Now, this noise generates a random vector for every point as soon as I connect the points. And if I now add these vectors to the original points, I move these points around. For visualization purposes, let's connect the point and the noise to an add operator and just use the result here in P. Nothing happens because I accidentally connected V. Be careful, because this is a little bit fiddly what exactly to connect. Switch this to original Perlin 2. Now you get this distorted plane. It's distorted by noise. If we dial down the octaves, you see that this noise is generating random vectors that are pushing the points around. Great, so what happens if we use these points as an input to our noise? If we do so, and reconnect our displacement effect, I can warp my noise, because I warp the input space, and the strength of the warping is controlled by this amplitude of the second noise. So if I set this amplitude to 0, we are back to the original Perlin we had. But if I now up the amplitude, you see that everything is warped around by the second noise. So by doing this, I can bend the input space, so to speak, and introduce new, more interesting structures. And now we have a machine to shape our noise as we wish. So with these operators in place, we really can do pretty much everything to our noise, and we can generate pretty much all noise effects that you have ever seen by doing this. You can shape your noise or warp your noise with a second noise on the input space. Then you can decide if you want to fold it or not. If I go down here, this is the unfolded version. This is the folded version, which gives us these veins, and then we can remap it using the ramp. And if we create a second stream of noise, we can then composite the values together to add a little bit of randomness. For example, if I lay down another terb noise, set it to original Perlin, like so. Let's quickly connect it up to see what it does. Sorry, that was a wrong connection. I want to connect it here to the amount of the displacement. You see that the Perlin maybe increase the octaves. Now I have small details, and now I can add this to my noise from before. So here's my noise, then I add this noise to it and use that for the amount, introducing little details to my noise. And this is really the standard technique to work with noise. So remember this, you will need it in the future. You can use this for shading, you can use that for generating colors, for creating terrains, for doing displacement effects on objects.